All right, circular motion problem for you. So we have here three cars that are driving at 25 meters per second along the road shown in the figure. So car B is at the bottom of a hill and car C is at the top of a hill. And both hills have a 200-meter radius of curvature. Suppose each car suddenly brakes hard and starts to skid. What is the tangential acceleration? That is the acceleration parallel to the road for each car. Assume that the coefficient of kinetic friction is 1. So notice that car A is moving on a flat road. There's no curvature where car A is. So car A doesn't have circular motion. Car B and C are moving in a circle, so they do have circular motion. So let's start with car A, which is going to be the easiest one. So let's do the sketch here. So that is car A. We have the force of kinetic friction because the car is skidding. The normal force with the road, Fn upwards. We have the weight of the car and friction to the left. So the acceleration of this car, because the only horizontal force is the force of kinetic friction, is going to be to the left. And they're asking us to calculate this. They're calling it the tangential acceleration, which is just the component of the acceleration that is parallel to the road. For car A, we don't have any other component. The acceleration is tangential to the road. But for C, B, and C, we're going to see that that's not the case. All right, so how do we deal with this? For car A, we have a free body diagram. So Newton's second law says sum of the forces in the x direction equals mass times acceleration in the x direction. The only force acting on car A horizontally is the force of kinetic friction minus mu k times the normal, and that's equal to ma. We're looking for A. We'd like to know how much is the normal force to be able to calculate A. So what is the normal force? The normal force is a vertical force. So to find out how much it is, you have to look at the sum of the forces in the y direction equals mass times acceleration in the y direction. Now the acceleration of car A in the y direction is 0 because we said the road is flat, so there is no vertical acceleration. The car is only accelerating tangentially. If it was accelerating vertically, and given that the road doesn't curve, then the car would lose contact with the ground. The car would take off, or the car would be digging into the ground. But that's not the case for A. A is moving in a straight line following the road, so there is no acceleration perpendicular to the road. So sum of the forces in the y direction is 0. Therefore, the normal force minus the weight equals 0, which gives us that the normal force is equal to the weight of the car. We plug it into the equation for kinetic friction, and we get minus mu k times mg equals ma. The mass is on both sides, and the acceleration that we get is minus mu k times g, which should be a familiar result to you. We discussed this in a couple of videos. So this is minus 9.8 because the problem says that mu k is just 1. So 1 times 9.8 is 9.8. Minus 9.8, the acceleration, because it's the car is slowing down, it's opposite to the direction of the velocity. We're using the positive x-axis to the right, the acceleration is to the left, therefore negative. All right, so we have our first answer that the tangential acceleration of car A is minus g, or minus 9.8. All right, we need to now move on to car B. So for B, we have a similar free body diagram. However, we're going to see the difference is that B is moving in a circle. So car B has the normal force with the ground, with the road. We're going to call it Fn. Car B has the weight, and car B has the force of kinetic friction to the left. Drawing the x-axis and the y-axis, and I'm going to add vectors indicating the acceleration direction. So for car B, we know that it's going to have a tangential acceleration in the same direction as kinetic friction. And this is the big difference with car A. Car B has a vertical acceleration. Car B has a vertical acceleration. It has a centripetal acceleration. The center of the circle is above car B, therefore there is an acceleration that goes up. You might say, but wait a minute, you say that for car A, if there was a vertical acceleration, the car would be taking off the road. For car B, there is a vertical acceleration. The car wants to go up, but the road is also curving up. So the car doesn't lose contact with the road, even though it has a vertical acceleration. If car A had a vertical acceleration, given that the road does not curve up, car A will be a plane taking off the runway, which is not the case. So car B has a vertical acceleration. So all of these cars are moving at 25 meters per second when we slam on the brakes. So we could calculate how much is the vertical or centripetal acceleration for car B. It would be v squared divided by r. So replacing the numbers, 25 squared divided by 200, the radius, gives us 3.125 meters per second squared. So this is the vertical acceleration of car B. So notice that the normal force is not going to be equal to the weight of the car. If the normal force was equal to the weight of the car, then what would be the vertical acceleration? It would be 0. If the normal force was equal to the weight of the car, the vertical acceleration of the car would be 0. That would make it impossible for car B to move in a circle. Car B would just dig into the hill instead of following the road upwards, curving upwards with the road. Car B would move straight horizontally, no vertical acceleration, so move horizontal and make a tunnel through the hill. That is not what happens to car B. So we know that the normal is not going to be equal to mg. So how much is the normal? Just use Newton's second law. What else is there to do? So Fn minus mg, Fn is positive, weight is down, negative, equals the mass of car B times the acceleration of car B. We just calculated the acceleration is 3.125. It is positive. So we have that. We plug it in there. So what is the normal force for car B? It's mg. We're moving mg to the right hand side with a positive sign. It's mg plus m times 3.125. So that's going to give us the mass multiplied by 9.8 plus 3.125. So m times 12.925. So now we know the normal force. So now we move on to calculating the kinetic friction, which will give us the tangential acceleration. So in the x direction, the sum of the forces in the x direction for car B, we only have one force. And that one force is going to be equal to the mass times the acceleration. So minus mu k times the normal, which is m times 12.925 equals ma for car B. The mass cancels. And the acceleration for car B is going to be, replace mu k 1, minus 1 times 12.925. And this is your final answer. The acceleration, tangential acceleration of car B is minus 12.925 meters per second squared. All right. Moving on to car C. So car C, we're going to do the free body diagram. I'm reminding here with these dots that the car is at the top of the curve. The normal force with the road goes up, the weight of the car goes down, and friction goes to the left. The acceleration, tangential acceleration, is to the left. I shouldn't have called it C. I should call it tangential. I think I did it in a second later, but anyway. And we have the, what is this vector, red vector that I'm drawing here? This is going to be the centripetal acceleration that car C has. Car C is moving in a circle. Where is the center of that circle? Below car C. So in what direction is the centripetal acceleration? It points down into the ground. So that is the centripetal acceleration for car C. So we're going to look at the vertical forces to get an expression for the normal force. And then once we know how much is the normal, we plug it into the equation for Fk, and we'll find the tangential, just like we did in previous problems. So in the vertical direction, sum of the forces in the vertical direction equals mass times acceleration in the y. in the vertical direction Fn minus mg, and the mass equals m times, what is the centripetal acceleration? Centripetal acceleration is v squared over r, but be careful with the sign. We know the acceleration is downwards. We're calling everything pointing up is positive. So Fn, we put it as a positive force, and we put mg as a negative force. So the acceleration has to be plugged in this problem with a negative value. So it's going to be minus v squared over r. So Fn equals mg, moving mg to the other side, and the minus, we put it in front, minus the mass times 25, that's the speed of the car, squared divided by 200. So m factor of g, 9.8 minus 3.125. And finally, the normal force is therefore m times 6.675 meters per second squared. That is less than mg. So the car, basically at the top of the hill at point C, the car has an effective weight less than the regular weight of the car. The car seems lighter. Everybody inside the car will feel a little lighter than the normal weight that they have. Similar situation that you would have if you were in an elevator and the elevator was accelerating downwards. Car C is accelerating downwards. So the same kind of feeling of less weight or being lighter would be happening to the people in car C. Alright, so we have the normal force. So now we can plug that result for the tangential acceleration, which needs the tangential force, which is the friction. Friction is mu k times the normal. We have the normal. We put a minus for friction because it goes to the left. So minus mu k times the normal. The normal is m times 6.675. And we're divided by m because net force divided by m is acceleration. The mass cancels. And the acceleration for car C is minus 6.675. So we have calculated all the tangential accelerations for the three cars. Again, I chose this problem because it is a good problem to point out to you, to make it clear that you have to be careful when you're doing circular motion problems in drawing the direction of the acceleration, in taking into account the fact that an object moving in a circular trajectory would always have a centripetal acceleration. It might have a tangential or not. In this problem that I did, there is a tangential, but whether there is tangential or not, that has nothing to do with the centripetal. Centripetal acceleration will be there simply because the object is moving in a circle. And the fact that there is a centripetal acceleration would affect the forces in this direction, in the same direction, in this case the vertical direction. So the normal force in car A, car B, and car C has a different value. Even though the cars might be identical, same mass, the normal force is not the same in car A for car B and car C. Okay? All right? I'm going to leave it there.